Hi, and welcome to the problem session for Lecture 12, covering eigenvalues and eigenvectors, matrix decomposition, and Markov chains. This instance is a problem session. We're going to leave aside all the details of the substance of these things and focus on computation. We're going to do one example of each type. The first one we're going to do eigenvalues and eigenvectors, and we're going to use an example from the book. The reason is that's actually worked out in the worked solutions for the book, but it's a nice example because it comes up with nice clean eigenvalues and also gives a nice example of how to compute eigenvalues and eigenvectors for a 3x3 matrix. Okay, so we start off with A, which is right here. Now we're going to compute the matrix A minus lambda I, which basically amounts to subtracting lambda from all the diagonal elements. Then we're going to take the determinant of that thing. So expanding on the first row, we get 2 minus lambda times the determinant of this thing, which is 2 minus lambda squared. Then the next one is going to be minus 1, because remember there's a minus 1 to the I plus j in front of each of the determinant terms, and this is the first row, second column. 1 plus 2 is 3. That's an odd number. We get rid of the first row and the second column, and we're left with 2 minus lambda minus 0, and then the next one is 0, so that's just plus 0, and that's going to equal 2 minus lambda times 2 minus lambda squared minus 1. We can expand that out some more to get 2 minus lambda, 3 minus 4 lambda plus lambda squared. And then it turns out we can factor the second thing into lambda minus 3, lambda minus 1. You can see that because there's a 3 here, so we have to multiply 1 times 3 to get that 3. And we have minus 4 times lambda, so if we have a minus 3 and a minus 1, we get negative 3 minus 1 is negative 4, and it works out. So here we have our factored thing. That tells us we have 3 possible eigenvalues, with 3 eigenvalues, 1, 2, and 3. So there we've now found the eigenvalues of this matrix. Now we're going to find the eigenvectors. So for each one, we're going to set up an equation. We're going to solve the equation that looks like this for each eigenvalue. And we're going to start off trying this x, 1a, b. We might have to change that around because here we're forcing the first element to be 1. In some cases, we can't do that if, for instance, the associated eigenvalue has a 0 in the first element. So in some cases, we'll have to try this again with different placement for the 1, but here we'll try this first. Okay. So this is going to give you a system of 3 equations and 3 unknowns, and each one looks like this. So when you multiply a times x, you get 2 plus a equals lambda is the first equation. And the second equation is 1 plus 2a equals lambda a. And the third equation is a plus 2b equals lambda b. Now the 3 equations, 2 unknowns, we have too many equations, so we can ignore some of them. And we'll go in order here. So let's try lambda equals 1 first. For lambda equal 1, the first equation implies a equals negative 1, as does the second equation. And then the third equation, when you plug in negative 1 for a and lambda 1 for lambda, gives you b equals positive 1. So that implies the eigenvector for this matrix, for this eigenvalue rather, is 1, negative 1, and 1. Now, if I was a little too fast, pause here, stop, make sure you can solve these equations and get those a and b out of there. Okay, now we're going to skip 2 for a second because we have some issues. Let's start with 3. Here is 3. Now for 3, we have the first equation implies a equals positive 1. You plug in the second one, you get positive 1 again. The third equation will then imply for a equals 3 that b equals 1 as well. And that implies we have 1, 1, 1 as an eigenvector for for lambda equals 3. Now let's do lambda equals 2. Now lambda equals 2 is potentially an issue because for lambda equals 2, turns out if you put lambda equals 2 here, you get a equals 0 from the first equation. But then the second equation would imply 1 equals 0, and that's obviously not true, so we can't do that. So instead, we're going to have to choose a different setup for there. So we're going to try instead putting the 1 in the bottom. So now the 1 being in the bottom, this gives you a system of 3 different equations. 2a plus b equals 2a. This is for lambda equals 2, mind you, so we're only going to do that one. A plus 2b equals 2b, and b plus 2 equals 2. The last equation implies b equals 0. Then the second equation implies a equals 0, as is the first equation. So now we end up with a equals 0, b equals 0, which implies we have 0, 0, 1, which is why we couldn't have used 1 in the first element. So there we go. Now we have our 3 eigenvectors. Now normally I like to keep this on the same page, but because we're in our room, I didn't want to write that small, we're going to skip the screen, move to the next screen. You might want to write down these 3 eigenvectors, because we're going to use them now to diagonalize the matrix A. So write those down. I'm not going to take a moment because you can pause this, but now we're going to write the, what we're going to do is we're going to put these 3 eigenvectors into a matrix, to correspond to the eigenvector matrix that we're going to use to diagonalize the matrix A. Okay, so let's write that matrix Q. Here's the eigenvector corresponding to lambda equals 1, the one for lambda equals 2, and the one for lambda equals 3. Now we can find the determinant pretty simply here. Determinant of Q we can actually do really simply by expanding out the second column. It's a little different than our normal routine, but we can do that. The first one, so with the second column, the first one is 0, so that's gone. The second one is 0, so that's gone. The third one is 1. There's a negative 1 to the I plus j there, because I plus j here is third row, second column. That's going to be 5, so it's a negative value here. And then we get rid of the third row, the third row and the second column, and we multiply it. 1 plus 1 is 2, so we end up with negative 2. So the whole determinant is negative 2, which we did by expanding out the second column again. You can try this yourself, expanding out the first row until you get the same answer. Okay, now we need to find the minors of the matrix. We need the inverse of Q. So the minors are the determinants of each individual part. M11 is going to be the determinant you get from removing first row, first column, is 0 minus 1 is negative 1. M12 equals what you get from taking the expanding out from the first row, second column, which gets us negative 1 minus 1 is negative 2. M13 is going to be first row, third column is negative 1. M21 equals second row, first column. Second row, first column is negative 1. M22 is second row, second column is 1 minus 1 is 0. M23 is second row, third column is 1. Again, I'm going pretty fast here, but again, you can stop and you can pause and check to make sure this out. You understand what's going on exactly, and this is all working out for you. Okay, third row, first column is 0. 2. Third row, second column is third row, second column is 2. 1 plus 1 is 2. And finally, third row, third column is 0 minus 0 is 0. So there we go. Now we will take, and I'll skip a couple steps here. We will take, well, you know what, I'll write this out. So now we write the conjoint matrix, which is the same as the minor. You put all the minors in the spots, but now put negatives in front of the ones that have a row plus column number being odd. So we have 0, that's negative 1, 2, negative 1, 1, 0, negative 1, 0, negative 2, and 0. Now we're going to flip these because we want to transpose, because the inverse of Q is equal to 1 over the determinant times the transpose of the conjoint matrix. So we got negative 1, 0, 0, and the diagonal stays there. We get 1 and 2 over here. We get 0 and negative 1 over here. And we get negative 2 and negative 1 over here. And we are done with that. Finally, to The diagonal matrix is the diagonal corresponding to all the eigenvalues. So that's 1, 2, 3, because we were careful to put them in order in the queue. And then finally, we have now diagonalized our matrix. If we take the matrix A equals Q diagonal Q inverse, we find that in fact we get A back again, and you can go check that at home yourself to make sure that it actually works out the way it should. Okay, so there you go. That's how you find the eigenvalues for a 3x3 matrix, find the eigenvectors corresponding to them, and then use them to diagonalize the matrix should you choose to do that. And there are more examples in the problem sets and in the book as well. Okay, so that's that topic. Now we're going to move on to the topic of Markov chains, which is very similar in a lot of ways, frankly. Okay. We're going to consider this transition matrix. Now we have a lot of fractions because remember that the columns in this case all have to add to 1. Everything must go somewhere when they transition. This one's not from the book. This is a new one. Okay. So, first question, is it ergodic? So does this Markov chain represent, this Markov transition matrix represent an ergodic stochastic process? The answer is yes. It's ergodic because it's aperiodic. You can always stay in a state you're in, you start in, right? Because all diagonal terms are non-zero, so you can always stay in a state you start in. And it's also ergodic because it's aperiodic. Because all states communicate. You can go from any one state to any other state just fine. Okay. So it is ergodic, so we should expect a unique steady state, a unique limiting distribution from which the system converges to from all initial conditions, which is good. It means they have a nice clear meaning for what's going to happen in this stochastic process represented by this Markov chain. To find that steady state, we're going to solve this matrix equation. So basically another eigenvalue equation with the value corresponding to 1, because it's a steady state, nothing changes. The vector we're going to use here is 1ab. We'll try that first again. We can write the equations out this corresponds to. We have 1/3 a plus, 1/3 plus 1/6 a, got ahead of myself, plus 1/6 b equals 1. We have 1/2 plus 1/6 a plus 1/3 b equals a, and finally 1/6 plus 2/3 a plus 1/2 b equals b. Okay. To solve these simultaneously, it's not quite as obvious as, well, it's not very obvious at all in this case, but we can try to get rid of some variables. What we're going to do is we'll take the second equation, subtract a from both sides, which would then produce 0 over here and a negative 5/6 a. Then if we multiply the first equation by 5, we'll have 5/6 a. We'll add that to the second equation. So we'll take 5 times the first equation, add to the second equation with its negative 5/6 a, and if we do that, we end up with this outcome, 1/3 minus 1 plus 5/6 a minus 5/6 a plus 5/6 b plus 1/2 plus 1/3 b equals 0. Or if you go through and deal with this whole thing, you get b equals 17/7. Okay. So there we go with that. And that gets us b. We can plug that b into equation 1 again, which gets us a equals 11/7. We can put that into pi, which gets us 1, 11/7, and 17/7. Or we can normalize it to get us the one in which everything adds to 1, 1/5, 11/35, and 17/35. Now this is normalization that's a little different than the normalization for a vector length. We're trying to make the length 1. We're trying to make the sum of all the components equal to 1. Okay, so there you go. There's an ergodic process, and we get a steady state, and that's the process we do it in. Let's now do one more example that is not ergodic. Well, it gives you the answer. Let's try this one here. Okay, so now note the second state, even though it's aperiodic, you can always stay in the state you're in, the second state does not communicate with any other state. Further, no state is distinguished. You can't get to the second state from either the first or the third, and you can't get from the second to either the first or the third. I mean, you can't get from this. Yeah, that's right. So this is not ergodic. And what you actually end up getting here is basically two distinct processes. If you're in the second state to start off with, you stay there forever. And any chance, so any basically probability associated with that state just stays the same. If you're in the first or the third state, then you end up moving into the steady state associated with those states. So basically, you can treat the whole thing as two separate systems and make a sort of m prime equal to 1/3, 1/6, 2/3, and 5/6, which is basically the matrix without the zeros and the 1. This case, you can find the steady state for this case. How do you do this? Well, again, you can make the matrix, the vector 1a, and you get the equation 1/3 plus 1/6 a equals 1, which implies a equals 4, which implies the steady state in this case is 1/5, 4/5 after being normalized from 1/4. Okay, so there's a steady state, which tells you any probability associated with states 1 and 3 ends up in that ratio. Now, if we start off with any state in which there is C in 0, 1 probability of being in state 2, that's the middle state, that means you have some sort of initial conditions that look like this. So there's 1 minus C probability of being here, and figure there's D and 1 minus D chance of being in these two, and C in the middle one. If you start anything in any initial conditions that look like that, you end up with the steady state that looks like this. 5C, and then 4 times 1 minus C over 5. That gives you a general steady state for the whole thing, and it tells you that the system is history dependent, entirely history dependent. If C equals 1, then the steady state is 0, 1, 0. If C equals 1/2, the steady state is 1/10, 1/2, and 4/10, and so on. And you can determine any steady state you want by knowing how much probability is in the second state at the beginning of the system's run, the initial conditions, and how much is not in 2. Note that the D we stuck in here, which was the probability of being in state 1 versus state 3, doesn't come up. The system's ergodic with respect to states 1 and 3, so the initial conditions aren't relevant for the steady state in that case. But they are relevant for the overall steady state because the overall system, including state 2, is not ergodic. So again, one more time, the final steady state will depend on the chance of being in state 2 in the initial conditions, that's C, because you can't enter or leave state 2 in any way. So how much chance you have of ending up in state 2 depends entirely of the chance you have of starting in state 2. And that's why the C stays here. The 1 minus C over here is to tell you if you're not in state 2, you have to distribute the rest of the probability, 1 minus C, among state 1 and state 3, and the final steady state distribution there is dependent upon how the system progresses because it is ergodic with respect to states 1 and state 3. And there you go. Okay. And that is the end of the problem session for lecture 12. Thank you very much.